machine learning crash course. Today we want to talk about robustness regression. Robustness regression. Okay. What is robustness regression? So it means that we want to fit a regression model, but in the presence of corrupted data, or we call them outliers. So when we have a least square problem, the data were something like this, then we found this line. It is supposed to be a line, but let's say we have some outliers in the data. So the data are something like this, but we have something like this data in here, and we want to find actually this line. But if you use least square problem in this setting of data, when you have outliers or corrupted data, then you will probably find this line as your least square solution. So actually we want to, the aim of robustness regression is to find a regression model in the presence of this kind of outliers or corrupted data. So we call these outliers, and they play an important role in the raw data, or in many competitions, like in Kaggle competitions data. There are lots of outliers that you should be aware of, or in the pre-processing step you should detect them or remove them. And also in the training of your model you should know how to handle these outliers. Okay. So outliers have different aspects. For example, they could be in different directions. The direction could be X or Y. So we could have a noise in this direction, and also we could have an outlier in this direction. Okay, so this will categorize the direction of outliers. And also another important factor in outliers is that fraction of outliers is important. Actually, fraction of outliers or number of outliers is important, but also the amplitude of error is also very important. So it means that how much they are outliers. So let's say if we have something like this, this is the solution, and we have several outliers in here, but they will probably not change the solution so much. They are not so bad. But if we have few outliers, but the amplitude of error will be high like this, then we will probably have trouble. So we should take care of different situation that we are faced with. Okay. In general, robust fitting is actually in high dimensional setting is very hard, and probably robust regression models probably not gonna work. So unfortunately, probably you could not handle outliers in high dimensional space. So you should try to somehow remove them with your expert knowledge, or something like this, or use another methods to remove the outliers before training your model. Okay, but for robustness regression, we will introduce to three different methods. The first one is Ransack. It is the abbreviation of random sample consensus, which we will talk about that. And the second one is Huber regression. And the third one is Thiel-Sen, which actually we don't talk about it so much. We just introduced that it exists, but we don't talk about it so much in here. Just mention that exists and you could use that. Okay, what is Ransack? So now we want to talk about Ransack. In Ransack, actually, what you do is choose randomly a subset of your data set, then and the number of the data in the subset should be the minimum number that you need to fit a model. Then, so first you should randomly select, let's say, m number from dataset, and the m is the minimum number of the data that you need to fit a model. For example, if you want to find a parameter of a line in 2D space, then you have two parameters, right? So and you know the equation of a line is something like this, and the parameters are a and b. In this case, you need two equations, so you need two data points in here. So in this case, m will be 2. Okay, so if your data set has 100 data, then you randomly select just 2 points to fit a line to these points. After that, you set a threshold, and based on that threshold, you specify inliers and outliers. Okay, and so if these are the data, then let's say we select this one and this one, then we fit a line to these two data. Then we setting the threshold, we could say that, for example, in this region, whatever data we have is inlier. So this is inlier, 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 but this is outlier, outlier, and outlier. Okay, so we do this for n times. Okay, so this is the first time. In the second time, again, we randomly select another 2 data points. Maybe it is this one. Then we calculate the inliers and outliers again. After that n times, we choose the model with maximum inliers, and then based on that maximum inliers, we fit a model to all of those inliers. Okay, so probably in this problem, let's say if your data is something like this, then you have some outliers in here. So let's say you probably choose these two as the first trial, and you have 1, 2, 3 inliers if you set a proper threshold and 2 outliers. With calculation of these two, also you have in total you have 5 inliers. Okay, and but if you select these two, then your line will be probably something like this, and you have 1, 2, 3 probably outliers and 1 inlier. So 1 inlier and 3 outliers, and so on. And then you will probably at the end you will probably choose this one. So you know that these points are inliers. So based on these inliers, you fit your model to all of these data points. So you will probably end up with this as your last solution. So you ignore this outlier. So this is how Ransack works. Okay. So let's say the number of iterations. We want to see how many actually trials that we need to ensure that we have a proper model without outlier. So let's say the number of iterations is n, and we want to choose that high enough to ensure the probability p means that it is the probability of at least one of the sets of random samples does not have or does not include an outlier. Okay, and we could represent the u, the probability of any selected data point is an inlier. So this is the probability of data being inlier, and so v is 1 minus u is the probability of having outlier. Okay, so for n iterations, you could easily write 1 minus p is equal to 1 minus u to the power of m to the power of n in total, and n isn't all number of iterations that we have. And if you calculate n from here, then you could actually derive a number for maximum iterations that you need. Okay, so this is the number of trials that you need to have a proper model. Okay, so this is Ransack. Actually, it is pretty straightforward, and also in Scalearn you could use Ransack, and we will see that actually at the end of this session to how it works in Scalearn. Okay, so the second method that we want to talk about it is Huber regression. So in Huber regression, actually it applies a linear loss to samples that are classified as outliers. So if you actually look at the Ransack, we ignored the outliers when we wanted to fit the model. But in Huber regression, we consider them, but we apply a linear loss to them. So a sample is classified as inlier if the absolute error of the sample is lesser than a certain threshold. So you set a threshold in here, then it calculates whether a point is inlier or outlier. Then actually in here it does not ignore the effect of inliers like Ransack that I mentioned that here, but gives a lesser weight to them. So loss function of Huber regressor is something like this. So we want to find the minimum of W and sigma, sum over all data points, h of epsilon, which is the Huber function, and epsilon is the parameter that you should select and specify. Plus, and as you know, it maybe sounds like ridge regression, but it is actually different from ridge regression. Okay, and if you plot the Huber function is something like this. So if this is the squared error, so this is the squared error x2, then for Huber function you have something like this to here. Let's write that first in here. H of z is equal to z squared for the absolute of z is less than epsilon, and 2 epsilon absolute of z minus epsilon squared otherwise. Okay, so in here it is like the squared error, but in this region it is linear, and also in this region because of this absolute. Okay, and the width of this region depends on the epsilon that you could specify that. Okay, so this is epsilon. Okay, and if you use actual Huber regression, you could build a robust regression model that could resist for the outliers. Okay, the third method is Thiel-Sen estimator, that we actually don't want to talk about it so much because we don't use it so much. We either use Ransack or Huber function. So yeah, we just want to mention that it uses a generalization of median in multiple dimensions. So it is robust to multivariate outliers, but the robustness of the estimator decreases quickly with the dimensionality increase. So when you increase the dimension in this method, the performance decreases very quickly. And so in high dimension, it will be like the least square error in high dimension. So actually we will not use that, as I said, so much. Also for Ransack and Huber regression, maybe we don't use them so much in the machine learning part, or when you have high dimensional data. But sometimes, especially in computer vision or image processing, we will see that we need some robust models that do not have very high dimensional data, but we need them to be robust to the noise and outlier. So in those cases we use Ransack. In fact, actually Ransack comes from the computer vision community, and it is invented by computer vision community. Okay. Let's see an example of each method in scale-learn and have some kind of intuition about how they work. For Ransack, as you could see in here, you could actually import that with just one line of scale-learn, and then you just use the regression, the make regression, to generate some data, some synthetic data. Then you just need to fit your regressor, which is Ransack, on your data. Okay, but probably with just like this, you have not very great intuition about Ransack. So there is another example of Ransack in here. It is a great example of how Ransack actually works. So you could see that we have some outliers in here, and so these are the data, and actually we want to estimate this line because we know that these are outliers. But if you use linear regression or least square problem to estimate the solution of parameters, you will end up with something like this line because of these outliers. But if you use Ransack, you could see that the solution of Ransack is so much better and more accurate than the linear regressor in here. Okay, and this is how Ransack works. And actually you could see that there are different thresholds that we talked about them that you could actually change if you want to customize the Ransack, such as that threshold or mean samples and also other parameters. But as I said, we don't need to so much tune the Ransack regressor commonly. Okay, the next one is Huber regressor. So in here also you could use Huber regressor, and you just create an object from Huber regressor, then fit it on your data. Let's see the parameters of the Huber regressor. So as you could see, the most important parameter of Huber regressor is epsilon, which determines the shape of the Huber function. So if we increase the epsilon, so let's say so the Huber function with something like this is from here, this is linear. If we increase the epsilon, then let's show it in here, we will end up with wider range of squared. After that we will end up with linear thing. Okay, so when you increase the epsilon, then you will have much larger region for the squared error regime. Okay, and that is alpha, which is the second term for actually regularizing the model, as you could see in here. Yeah, and that is Huber regressor. So you could use it very easily in scale-learn. And let's see the result of also Huber regressor versus Ridge regression in here. So if these are the data, these blue points, so we know that this is this one, and these are probably outliers, and so we know that intuitively the right solution is something like this red line or blue line in here. But if you use Ridge regression, so if you remember that Ridge regression means that least square plus regularization parameter. Okay, so if you use Ridge regression, then the solution will be something like this, which is not actually really good. So, and this is not actually correct intuitively. So you could actually use Huber plus, so these are different epsilons for Huber function. Then you have these lines, which are the lines that we want in here, and actually you could see that if you increase the epsilon, then as you increased it, you may close the solution to the solution of least square or Ridge regression problem. Okay, so we talked about the Huber function based on the epsilon. So it is important to tune the epsilon parameter for Huber loss, which is for the default of scalar, it is 1.35 the epsilon value. Okay, and the Thiel-Sen regressor is, let's see how to use that. It is also for using that, you just need to import that from linear models, and like other, you just fit it on your data, and this is the result of using Thiel-Sen. Let me to zoom it for you. Okay, and you could see actually one of the benefits of Ransack is that it is so much more it is actually quicker than Thiel-Sen. Okay, it is much faster than Thiel-Sen algorithm. So it is actually in a very short time you get the Ransack output, but for Thiel-Sen it took about 0.6 seconds to get the output. Okay, and these are the results of Thiel-Sen, and this is the Ransack. As you could see, maybe it is not so much difference between Thiel-Sen and Ransack solution. Okay, but with Ransack you have a very good performance and runtime complexity when you want to apply that on especially large data sets. Okay, yeah, so that's it. I think now you know how to use robustness regression, and more importantly, you should know what is outlier. It is more important than the robustness regression itself, because as I mentioned, maybe as the dimension increased, then you could not probably use robustness regression methods, but you should know how to deal with outliers, because they could ruin your classifier or your regressor so much. And actually, if you want to compete in Kaggle competition or any other competition, one of the most important steps for data scientists or machine learning engineers that they work on in pre-processing step and in cleaning data is detection for outliers, because outlier detection could actually increase your performance and your accuracy so much. So please be careful about outliers, and you could actually read lots of materials online to how to detect outliers. And yeah, but for just few dimensions, you could use robustness regression to mitigate the problem of outliers. Okay, hope that you enjoyed from this session. See you in the next session. Bye.